Hello everyone, welcome back to my channel. So today we are going to discuss about explainable AI, and this is going to be a three-part series. So let's start with the introduction of explainable AI. Okay, so this diagram here shows a common issue with AI systems. You give it an input, say a picture of a dog, it goes into this black box and comes the result dog. But here's the question: how does the model know it's a dog? And that's what explainable AI is all about, understanding what's happening inside this black box. Because think about it, if we don't know how the model reaches its decisions, how can we trust it? And this is especially important when AI is used in fields like healthcare or law, where understanding the why behind the result is very important. And that's what we are going to do in the next upcoming videos, is to see how we can open up this black box and make sense of what's inside that. So we just talked about the black box problem in AI. Now let's see what explainable AI or XAI actually does. So if you look at this diagram, it's no longer just black box, right? Instead, you can see the steps that model takes to arrive at the output. And each node here represents a decision or a calculation the AI makes to figure out, in this case, that the picture is dog. So just consider it like a decision tree wherein you can clearly see the path. And the goal of XAI is to make these processes more transparent. So instead of just saying dog, the model can explain why does it think it's a dog. Alright, now let's look at how explainable AI visualize what's happening inside. And this is one of the real world examples that we have taken. And this image shows something called as heat map. So the highlighted areas in red and yellow, and these are the parts of the image the AI focuses on to make its decision. So for example, in the first row, it's looking at the faces to identify them. In the second row, the AI seems to be focusing on the body of the dog. And this is what makes explainable AI so powerful. So we can literally see what parts of the input matter the most to the model. And this is critical for spotting errors or biases that the model is making. Alright, now let's talk about the building blocks of explainability, and we'll break it down into three simple steps. So first, obviously we need a model that can predict something. In this case, whether a loan application will be approved or not. And for example, here we have John and Alex. So based on their income and credit scores, the model predicts that Alex's loan is approved, but John's is denied. Step 2. Now once the model makes the prediction, we need to understand why. Why did the model deny John's loan? So this is where explainability really starts to matter. And we'll dive deeper into this in the next video in the series. Finally, it's not just about understanding the why, it's also about providing some actionable advice. So for example, we can suggest that if John increases his credit score to say 720, his loan could be approved. So moving from explanations to recommendations kind of thing. Now let's talk about some of the categories of explainable AI. So these category helps us understand different approaches to making AI models more transparent. And let's break them down one by one. So let's start with intrinsic models. And these are basically where explanations are built directly into their design. So take decision trees, for example, right? They are inherently interpretable because you can see like the entire path of the model that takes to make a specific prediction. So in this case, the model uses features like age, weight, smoking status to determine whether someone is at high or low risk for a heart attack. So these models make it easy to understand the why behind a prediction without any extra tools. And the explainability is kind of built into the model, and we can use the existing tools that the model has to see why the model made that particular prediction. Now let's look at post hoc explanations. So unlike intrinsic models, these explanations are added after the model is trained. For instance, tools like SHAP are often used to explain the outputs of complex models like neural networks. So let's start with global explanations. So these focus on explaining the behavior of the entire model. For example, in this table, we can analyze trends across all the loan applications. So, for instance, we might see that higher credit scores generally lead to higher approval percentages. Now, let's move to the local explanations, which focus on specific predictions rather than the entire model. So, for example, look at this row where the loan application had a 40% approval likelihood. And local explanations can tell us why this happened. And in this case, it might be because the applicant's low credit score of 680. So the next is model agnostic methods, and they work with any model no matter how complex they are. So, for example, imagine a bank using an AI system for loan decisions. So, a model agnostic tool could be something like SHAP or Lime, which can explain that decision no matter the complexity of that model. And model specific methods, on the other hand, are designed only for a specific model type. So, for instance, if the bank uses a simpler model like linear regression, you can directly use the model's variables to understand why it made that decision. Feature importance focuses on identifying which features most influence the model's prediction. For example, in a loan approval model, a feature importance graphs might show that income and credit score are the top predictors for approval. So this method basically answers the what and what factors drive the model's decisions overall. Whereas example-based methods explain predictions by comparing them to similar cases. So for instance, say if a loan is approved, the model might highlight other applicants with similar income and credit profiles who were also approved. So this method focuses mostly on why the model made a specific decision by pointing to relatable examples that are there. So let's take a look at the very first step toward model explainability, that is making predictions. So in this, I've taken a simple loan data set. Each row represents an applicant and features like age and loan amount and everything. And we can use any model that we want, like a logistic regression, random forest, neural network, whatever, to make predictions based on the data set. And the approved column shows the prediction outcome. So this data set kind of gives us a perfect starting point, which we can use in the next couple of series to understand all the steps of explainable AI. Now let's take a look at the trade-off between accuracy and interpretability when choosing models. So this graph nicely illustrates, a challenge that more accurate models are often harder to interpret. For example, neural networks and random forests are very accurate, but they are also harder to explain because of their complexity. On the other hand, simpler models like linear regression or decision trees, which are much easier to interpret, but are also very low on accuracy. So this trade-off highlights why explainability models are so important. So in the next video, we'll dive deeper into one of these explainability tools, SHAP, and try to understand what it is and the math behind it. So if you enjoyed this video, guys, please consider subscribing and don't forget to like the video. It really helps out the channel. And if you have any questions or want me to cover any other topic, feel free to drop your thoughts in the comment section. And I'll see you guys in the next one.